Higher order differential equations. So let me just get a big snapshot of this and have it in our notes. So the first section in this chapter talks about just some theory behind this and existence and uniqueness, and talks about two scenarios. One is the initial value problem, and the initial value problem is something that we may have seen before if you've taken Physics 260, which is kinetics, or if you've taken Calc 3, which does motion problems from, or even in Calc 2, when we have an acceleration, you have to want to find the original position function. That's all. That's what this is about. We have your acceleration is a second derivative, and then you take the antiderivative to get the velocity, and then you get an extra plus c in your integral, and then you use one of the initial conditions to solve for the plus c, and then you integrate again to get the position, and then you use the other plus c. So I think the only thing I want to change here is that this should be in parentheses. Oh, this is not subscript, superscript. All right. So the idea is that your differential equation is of nth degree, nth order differential equation. And your initial conditions should have information at a starting point, and that starting point has to be the same for all your initial conditions. So your initial conditions have a starting point, and then you have initial conditions starting from the original function all the way up to one less than the order of your differential equation. So if you have a fourth order differential equation, you should have initial conditions that go up to the third derivative. Okay? And we can look at the original function as if it was like the zeroth derivative. Technically, you're not taking the derivative of it, so it's the original function. So if you look at it that way, there's a lot of these things can be written nicely. So that's your IVP for your nth order differential equation. The existence and uniqueness tells us that if we have fairly nice functions that are multiplied by the derivatives of y, and it's continuous on some interval, and every x, so there's going to be a point in this interval that will be your initial value, then there's going to, you're guaranteed to have a solution. Now whether you can find it or not is a different story, but you know that a solution will exist within that interval. So if any of these things, a sub n plus 1 and all that, or minus 1, if any of these functions have discontinuities, then your whole solution will have a discontinuity there, or will not exist beyond that point. Does that make sense? Okay. So we're not going to prove the existence and uniqueness. You can go take your upper division differential equations class for that. But I think we should be able to identify the intervals that they're talking about. So let's take a look at like problem number 9. It says here, let's find an interval centered about 0 for which the given initial value has a unique solution based on what they say in that existence and uniqueness theorem. So I'm not too interested in trying to solve for this at the moment. But what I can notice, let's take a look at the theorem again. It's saying that an minus 1 all the way to a sub 0 and g is continuous on some interval, on that interval. And then x equals x naught is a point that's somewhere in that interval. Okay. Then you're guaranteed a solution, and the solution is going to be unique. So here we have our differential equation, our DE, and then these two are our initial conditions that make the IVP, initial value problem. So if I take a look at my functions, this would be like a sub 2 a sub 1 doesn't look like it exists because that would be multiplied with a y prime, and y prime is not there, so a sub 1 must equal to 0. A sub 0 looks like it's equal to a constant. And the other side, or the right-hand side, is our function x. And these are all continuous on all real numbers from minus infinity to infinity. And then we have a 0 here, which happens to fit in our all real number continuous interval. So it looks like we will have a solution there's a unique solution on the interval. Actually, it's on all real numbers, so we can rewrite our interval as minus infinity to positive infinity, and that's where our solution exists. Okay. If any of these had a fraction where the variable is in the fraction that would make that equal to 0, that would be bad. You know, that would just be a cutoff, when it means our solution is not going to exist with that interval. If we had a fraction like a 1 over x or 1 over x minus 1 or something where it would make it undefined or discontinuous. I thought it was just... Oh yeah, so the highest order one, that just defines the order. Because if a sub n was equal to 0, then it's not an nth order.
But what is that? Let it not be 0 for every x. What implies that?
Oh yeah. Oh yeah, let's scratch that. Let's try that again. What am I going to do? I'm going to erase some of this. Sorry. So, yeah, there's this thing about the a sub n, because you have to divide stuff out. So a sub n, or a sub 2 of x cannot be equal to 0. So x is equal to positive 2. All right, let's try this again. So if you have a point here, the reason why they do that is because a lot of times when you solve for this, you have to divide by a sub n. And when you divide by a sub n, then all these other functions will have a bad point when a sub n is equal to 0. So
if x is equal to 2, then
so this is where we want to break off at 2. And our initial condition happens to be at 0. So your unique solution will either be on this left side of the 2 or on the right side of 2. And since our initial condition has 0 in it, your interval where this exists is going to have to be on the positive side or on the right side of 2. Yeah, I think so. Boy. So we want to be on this side. Yeah. So the initial condition has 0 in it. So you want to take the interval up to and not including the break point, which is at 2. So unique solution on the interval from minus infinity all the way up to 2. So if you had your initial condition started at 5, then you would be on the other side of 2. And that would go from 2 to infinity. And then if you happen to have another 0 somewhere else, then you have several places to choose from. Okay?
We find out that x equals 2 is a solution for a equal to x 0, which just tells us that it's not continuous.
That it's not continuous. Well, your solution to your differential equation might not be continuous there.
And the solution to dE being the original function.
Yeah.
You say might not be?
Might not be. Usually not. I'm trying to think if it ever is.
Okay.
And I can't think of an example where it is.
Gray areas. Let's call it something.
All right. So that's the IVP. Let's take a look at the BVP. So sometimes a differential equation gives you information not about the original function and the first derivative at a point, but instead it gives you information about the starting point and ending point of something. So if you have a scenario where they give you information about the starting point, the original function starting point, and the original function's ending point, and they give you information from A to B, then this is called a boundary value problem. So the initial condition, initial value problem has the same x value and has the function and its derivatives. The boundary value problem has different x values. Now, it'd be nice if they have different x values and then they give you the different x values on the same function, but sometimes they give you the different x values on its derivatives, or they give you different x values on the function on one side and the derivative on the other side. So they have a lot of different scenarios here, and the boundary conditions might be a combination of functions, but they have to have different x values. So the main deal about this is that there's no existence in uniqueness theorem here. So you're not guaranteed to have a solution or a unique solution. And I think, fortunately, it doesn't happen as much as the initial value problem, so it wasn't really anything to pursue.
So you may not have a unique solution.
You may not have a unique solution. Or in some cases, you may not have a solution at all. And if you do have a solution, it may not be unique.
What does a non-solution look like?
It just means there's no value for, there's no function y that would make this
Continuous between the interval?
not even intervals. So you just can't find a function that would fit this differential equation, period. See, in the past, we've always, whether we can find it or not, we know that a function exists. Here, there's no guarantee that even a function exists that would satisfy this differential equation with the boundary conditions. So I think I wrote that somewhere.
At what point along the steps do you start to realize that there's probably not a solution?
I don't know. I haven't really worked with boundary value. I haven't really worked with boundary value problems much.
Neither have we.
The main thing here is to really, I think the process is to solve for this. The boundary conditions allow you to find your arbitrary constants. So, the process will be the same for the initial conditions and the boundary conditions, except when you do that, you solve for C. And here, you may not be able to find C values that work. So I guess to answer your question, we would have already have solved for the general solution, and then we just won't be able to find the C values. All right.
So we're guaranteed a general solution?
I guess you can say you're guaranteed that the general solution will exist. I mean, whether you can find it or not is a different story. So you'll be guaranteed a general solution, except when you try to solve for those C's, you might not get your particular solution.
I was just wondering if we were getting into territory that couldn't even solve that without the initial conditions.
Yeah, I don't think that'll happen, because the initial conditions and the boundary conditions all come after the general solution. All right. I hope that's all a theory. Let's be done with theory. Let's see. Just some examples. Hey, look at this example. That kind of looks familiar. All right, let's move on.
Well, maybe we should know. You know, see it.
All right, let's move on to the first type of equation we're going to be dealing with for higher orders is the homogeneous differential equation. Now, I know we talked about homogeneous differential equations as something with a y to the n or is that Bernoulli? What's homogeneous? You guys remember? So we do that substitution, x equals vy, right? So homogeneous is something where you put a t x and ty, and then you get the factor out of t, and then you get some t to some power. Anyways, this is different. This definition of homogeneous or homogeneous equation is saying that your differential equation is set equal to 0. So that would be more in line to the linear algebra's definition of homogeneous system as being set equal to 0. So this is what we're going to study first in great detail. We're going to study an nth order differential equation, and we're going to simplify even our study. We're going to simplify it to just looking at constant coefficients, where the functions here are just constants, the an, an1, a1, all that stuff. We're going to study where it's constant coefficients, and then we're going to have a nice algorithm to solve for these things. So if your right-hand side, if you have everything, if you write this in standard form, I think, where you get all your functions and its derivatives all to one side, and then you have your other function that doesn't have a y or any derivatives of y on the right-hand side. So if you have nothing left and that's equal to 0, then it's homogeneous. If it's not equal to 0, it's non-homogeneous. So, yeah, we're going to focus on the homogeneous portion first. Oh, yeah, and these are all linear, right? Because your y's are not being raised to a power, is not taking the sign. Now, your ax can be sines or cosines or powers of x. It's the y's and y primes are the ones that don't have those weird powers of x. They're not composed with any other weird functions. Okay? All right. Let's see if we can actually, when are we going to start solving problems? So here's just a couple of examples. The first one is non-homogeneous. The second one is homogeneous. Okay. Let's see if we can move on.
So in this example, the first one is not, the second one is.
Yeah. I think I'll mention this differential operator, but we were not really going to dig into this too much. But anybody who's taken Calc 3 and might have seen the del operator, it's kind of like working the same way. So we can use D as a symbol. And then what this allows us to do is we get to focus on the D. We can pretend that's even a variable. But D is called the differential operator, and that's what people tend to use when they want like a total derivative of something. All right, let's just pass this over. What's next? So there's more theory here. Let's see if we can try to understand what these things are saying. So a linear operator is a process that allows you to be able to add and multiply by a number, by a scalar. And you can split that up. You guys have probably seen something like this before. Like, where have you seen something like this before? In linear algebra? So linear transformations or linear functions or linear operators. Where else have you seen this before? Does it look really too cryptic for you? There's two that you know of. Maybe they're obvious. But two linear operators that you know of. Integrals. Integrating is a linear operator. What else? Differentiating is a linear operator. So L would stand for your linear operator. So in other words, if you take a look at L as the derivative, let's call it d dx. d dx of alpha fx plus beta gx. That's equal to alpha times d dx of f, or f prime, plus beta times d dx of g. We've seen that. You know, that's true, right? Integrals also the same way. The integral of alpha fx plus beta gx is it's like splitting this up. It's like taking an integral of a polynomial. You split it up and you take the constant out and you just do the integral of the power function. So it's just alpha integral of fx plus beta integral of gx. So these two are linear operators, and I'm sure at some point your calculus teachers might have tried to convey this information. I did when I was teaching Calc 1 and Calc 2. I said, oh, this is a linear operator. Anyways, there's a lot of linear operators that work in linear algebra. All those matrices work as linear transformations, linear operators, and you can factor out an alpha, and then you can split up the addition of things. So if you're in linear algebra, we'll see that sometime in the future. All right, superposition principle is a principle that we will be using a lot in this chapter. So let's take a look at this. You have an nth degree differential equation, or nth order differential equation. That means it has n derivatives. And you know k solutions. They're separate functions. They happen to be separate functions. Because differentiation is a linear operator. That's what we're calling it, right? Transformation operator. Because differentiation is a linear operator, and this is a linear differential equation, it turns out that the linear combination, or the alpha times y1 plus alpha times y2, or different alphas, then any linear combination would also work for this as a solution. Does that make sense? You can, this is a way of saying that you can kind of stack up your solutions. You find one solution that works and you find another solution that works. Well, maybe you can just add them up. Maybe you can just multiply them by a number and then add them up. And then that would also work. Is there an example? I was going to come up with an example. Let's come up with an example. Let's see if we can come up with something simple. I don't know. Can you guys think of any function whose second derivative is equal to the original function? Sine and cosine, right? Sine, the derivative of sine is, and derivative of cosine. Wait, but that's a minus, right? E to the x? The second derivative has to be the same. Yeah. E to the x is always a good one, right? That's always something where... So let's try e to the x. E to the x?
Maybe 1/4.
So with the 2x here?
Yeah.
Modify the other one.
Yeah.
So let's try this one. The first derivative is 2e to the 2x. The second derivative is 4e to the 2x.
Yeah.
So y double prime, that's 4e to the 2x minus 4 times y. What's y equal to? E to the 2x equals 0. So this works. Let's put a box around that. Can you think of another function that might work? Zero? Zero would work. That would be a trivial solution. Did I hear somebody say e to the negative 2x? Is that going to work? Y prime equals negative 2e to the negative 2x. Y double prime is equal to positive 4, right? So this also works. So I have two solutions that work for this differential equation, and so it'll turn out that if we combine these two things, if we add these two things, not only add them, but also multiply them by some constant, then this is also a solution to your differential equation. In fact, what if I change the constants to C1 and C2? So this is also a solution to the differential equation. And we can do this by taking the derivative twice and then plugging it back in there, and then we'll see that it'll work out. That's because the derivative of this, that's because the derivative is a superposition principle thing. In fact, the way you guys did this on your test, I graded about half of it. The way you guys did this on your test, you took the derivative twice, right? Let's do it real quick. So that's the first derivative, the second derivative. And then you put the second derivative into the top, and then you put the original function in for this, and we'll see things cancel. So I'm going to go through that, and I just want to show you how this might work in general cases, which is going to be, I think, slightly different from the way most of you guys did the problem on the exam.
This whole thing works because of linear operators.
Because of linear operators and the superposition principle works because it's a linear operator. I'm going to show that this is equal to 0. I put this back into y double prime minus 4y equal to 0. So you could see things cancel. Yeah?
So those constants don't need to be anything in particular. They could be anything.
They could be anything, right. So most of you just matched it up and canceled here, and then they said, oh, that's equal to 0, and that was good. But I wanted to regroup this a little bit differently. I'll take these two here, 4c1 e to the 2x minus 4 c1 e to the, one of them's a minus. What happened? This one? So I'm going to reorder this a little bit. So I collected those terms and just switched the order. And then for this first one, if I factor out a c, carefully putting my parentheses. A lot of these parentheses don't matter, but I just want to carefully place my parentheses here. Now, if I look at just that, that is the second derivative minus 4 times the original function. the second derivative minus 4 times the original function times some constant. But this is supposed to equal to 0, right? Because e to the 2x is a solution. And then I could do the same thing over here, c2, and then I collect the second derivative minus 4 times the original function so this thing is equal to 0 since e to the 2x is a solution. This thing over here is equal to 0 because e to the negative 2x is a solution. So this is how you would prove it in general. And in general, it could be a long, complicated proof, but this is an actual example. But if you look at it, these are just your derivatives in your original functions and stuff. That would make it equal to 0. All right. Let's move on. So there's more information that comes from the theorem. What theorem? If the superposition principle, if y is a solution, then a constant times this, times that function is also a solution. The trivial solution is always a solution for homogeneous because it's set equal to 0. We don't need this. I don't know why this is there. I think this was just an example. You guys know what a corollary is?
Speculate.
Sure.
It's like things that it implies, implications, deductions from.
Yes, awesome. Good. So when mathematicians build things, they have these postulates or something, that's things that they assume that they're true. And then they start building, when they start proving things, they have these things called lemma. Lemma is a small proven fact, or fact that can be proven. And then to get to the big things that they prove, they call those theorems. So when they're able to prove something big, that's a theorem. And then corollaries are things that follow from the theorem, things that you can imply. A lot of them still need to be proven, but some of them are obvious because of the theorem. It's just an obvious example, or it follows as a special case or something. So that's what this corollary is saying. All right, we got more definitions that are kind of linear algebra based. Linearly independent. You guys have seen that before?
Not necessarily on the same line. But now it makes more sense that we're talking about linear operators.
Linear operators.
The linear part is in math.
Yeah. And the linear algebra definition is exactly the same, except for linear algebra, a lot of times you're looking at vectors. So here you're looking at functions. So functions are linearly independent if, or they define dependent first, are linearly dependent if you can find constants that are not all equal to 0, so that the linear combination of this a constant times the first function, constant times the second function, etc., is going to equal to 0. If the set of functions is not linearly dependent, then it's said to be independent. So let's take a look at an example. E to the x and e to the 2x and e to the negative 2x. Those are the two solutions that we found earlier. So the question is, are these linearly independent? So my question to you is, can I find C1 and C2 Can I find C1 and C2 so that this would equal to 0? Actually, there is one. What's the one? So if C1 was equal to 0 and C2 was equal to 0, then that's the only way you can get that to equal to 0. So here, let me do an example of 3 functions. And ask you, is this linearly dependent? So the question again is, can I find a C1, C2, C3 so that the linear combination would equal to 0? What do you guys think? What would C1 be? -3. C2? 2. C3? 1. So would this work? This would be -3, +3 would cancel, C2 would be 2 times 1, and then there's a -2 here that would cancel. So yeah, this looks like it'll work. So in this case, what can you say about the functions x squared, 1, and 3x squared minus 2? They are, but they're linearly dependent. And what can you say about e to the 2x, e to the negative 2x? Linearly independent. Okay? So it turns out that when we're hunting for functions, it's important for us to know whether functions are linearly dependent or independent. Because if they're linearly dependent, then they're essentially the same function, except, you can just add or subtract a constant times something else, and so that's not going to give us any new information. Another common one is sine x, cosine x, and then sine 2x. If you think about that, that's also, those 3 functions put together are linearly independent. Or linearly dependent, sorry. Okay, so anyways, we'll see that we're going to be, whenever we're looking for an nth order differential equation, we're going to be actively looking for n linearly independent functions. Okay, let's move on. Wronskian. Wow. They're really putting all the theory up front here. Have you guys dealt with matrices before? If you haven't, here we go. The Wronskian is the determinant of a matrix that's built from a set of functions and its derivatives. So whether you write the functions across or going down, it doesn't really matter, because the determinant works if you're doing rows or columns. And in most cases, we're just going to be dealing with 2x2 matrices, which is nice. Every once in a while, we might need to dig down and do a 3x3 matrix, and find determinants of 3x3 matrix is not easy, but it's not that difficult. But compared to a 2x2 matrix, 2x2 matrix will be easy to deal with. So functions have at least n-1 derivatives. The Wronskian of the function is defined to be the determinant of this. So you construct a matrix, you find a determinant, and then the criterion that we're looking for is that if this determinant is not equal to 0, then it's linearly independent. And if it is equal to 0, then it's dependent. So the two examples that we did earlier, we can redo them here to apply the Wronskian. So we're going to do a 2x2 matrix with the first example of e to the x, or e to the 2x, and e to the negative 2x. And so the Wronskian for that, I'll just put w. Usually you would say w and then parentheses and list those functions down, but I'll just put w. You want to list down the functions in the top row and its derivatives in the next consecutive rows. So this one would have a derivative of 2e to the 2x. This is negative 2e to the 2x. And so this will allow us to go through the process of finding the determinant of the 2x2 matrix. So the diagonals are the ones going from left to right, going in the diagonal. And then the wings, they call them, are the other two numbers that are involved. So the determinant of w, I guess it's already defined to be the determinant. The Wronskian is going to be 2, let's start in order, e to the 2x times negative 2e to the 2x minus the product of the other ones, 2e to the 2x times e to the negative 2x. So e to the 2x times e to the negative 2x, I think, is just 1, right? Because one's on top, and it's a fraction. One's on top, one's in the bottom. So I have negative 2 times 1 minus 2, so this is negative 4. More importantly, this is not equal to 0. So that means these two functions are linearly independent. That's good, because that's what we concluded last time. Let's take a look at these three functions and do the Wronskian for that. And I'm just going to fly over the process of the determinant for this. It's 3x3 matrix and ask you to look up how to find the determinant of a 3x3 matrix on your own. So let's set it up the same way. We're going to write down the functions on top, and then we'll take derivatives after that. So 2x, derivative of 1 is 0. This is going to be 6x. Yep. And then one more derivative, 2, 0, and 6. Okay. Now to find determinants, there's several ways to find determinant. You can do what's called expanding on a row or a column, and you can choose whatever row or column you want. So I'm going to highlight, that's not highlight, highlight. I'm going to highlight the second column, and I like the zeros in the rows or columns that I'm looking for. And what I'm going to do is I'm going to expand on this one by one. So as I go through and take a look at the first one, oh, there's also a counting thing. This is really getting confusing now. Each of these has a sign. And so we have to also follow that sign. So like for the first one, I'm going to expand on the second column, and the second column will innately start with a negative sign. So -1 times, and now what I'm going to do is I'm going to cross out the row and column that it has, and then I'll take a look at what's left. I have a 2x, a 6x, a 2, and a 6. And then I want the determinant of that. So now it's a 2x2 matrix. And then next I would expand on this one, on the second number. So I'll have 0 times another 2x2 matrix that's going to be left after I cross out the row and column in which that belongs. So that's x squared, 3x squared minus 2, 2 and 6. Now I didn't have to write that because this is multiplied times 0 already, so this is like useless information. But I just want to show you where that comes from. And then the third number I have in my expansion is going to be 0 again, but this time it's a negative. Well, -0 plus 0 doesn't really matter. X squared, 3x squared minus 2, 2x, 6x. So in any case, those two doesn't matter. I have a -1 times, and then the diagonals minus the wings, so it's 2 times 6, 2x times 6. Hey, that's equal to 0. So these three functions put together are not independent, they're dependent, because your Wronskian is equal to 0 on any interval. So they're dependent because the Wronskian was equal to 0. All right? So most of the problems that we're going to be working with are 2x2 matrices, or we're dealing with two functions because we're solving for second order differential equations. But if you ever have to check for 3x3, one way to do it is to expand your matrix like I did, or there's other methods of doing this, and I'm just going to ask you to just Google it. Or take my linear algebra class. We're going to be doing determinants in a few weeks. So this is linearly dependent and independent.
Which is kind of,
If you look at it, it's like,
is it the same?
Uh,
English? Maybe just ran different methods on it, right?
yeah, yeah. The other one was just guessing and checking. All right.
Superposition?
Yeah, so
Too?
no, superposition is just a theorem that says that any linear combination of functions, it doesn't have to be dependent or independent, but any linear combination of functions would work as a solution.
But we get to use that
Yeah,
to determine dependence.
yeah. So here's where we start putting it together. We get a fundamental solution set for nth order linear differential equation. What you essentially need to do is you need to find n linearly independent functions. And the existence of a fundamental solution for any homogeneous linear solution exists on the interval, on the given interval that we defined earlier. So the take home here is that for nth order, and we have to go with the linear DEs to find the homogeneous the solution to the homogeneous equation. We have to find n linearly independent functions. Genius. So our key is to find n linearly independent solutions. So if we have a second order differential equation, we need to look for two linearly independent solutions. Okay? And how to check for linear independence? We use the Wronskian. And we know that the linear combination of them will be our general solution.
So pretty much just the Wronskian.
The Wronskian will help us determine if it's linearly independent. I think most of the time it will say one is sine x, the other one's a cosine x, so we know that's linearly independent. Or if you have e to the something and e to a different power, then we know that's linearly independent. But if we go back to this example that we had earlier, we have a second order differential equation, and then we have two solutions that we've shown were linearly independent. Then, according to the superposition principle, we have a general solution that's simply a linear combination of those two linearly independent functions. And we can do the linear combination by just putting a C1 and C2, and those will just happen to be our arbitrary constants. Okay, so all this builds up to all this talk about linear independence, linear combinations, linear operators, all builds into our solving our linear homogeneous nth order differential equation. So that gets us to our last part. Our general solution then will become a linear combination of all those linearly independent solutions. all built in with the arbitrary constants, using the superposition principle on linearly independent functions. Just sounds like all these linear combinations and independence, and it all sounds the same now.
Yeah, so these functions of y that are in this, they're all linearly independent.
So all the y's are linearly independent. So being a fundamental solution means that they're all linearly independent.
Okay.
And there's n of them, and our differential equation is an nth order differential equation. So when you have an nth order differential equation, you're going to have an n parameter family of solutions. And you have n different solutions. Well, it turns out that the linear combination of them, by linear combination, I just mean constant times the first function, plus constant times the second function, plus constant times the third function, etc., will form your general solution for the differential equation. And you would be able to solve for these constants if you have your initial conditions. But they have to be linearly independent, because if they're not linearly independent, then this linear combination is really just, you might be one or two functions off. You need one or two functions more. It has to be built from a set of linearly independent functions. Okay? Next time we actually get to solve for it. I mean, we kind of did some solving. We did some minor solving for things, and we did some examples of linear independence and stuff. But next time we can actually see these things get put into practice.
Remind me what determinants are n, the order?
The order, the highest derivative
Right.
is your n, is your order.
Order of the DE.
Order is differential equation is the highest derivative. All right, there's a lot to think about, or not. Go home and enjoy yourselves.